Good morning everyone. Welcome to the course Stability Aspects of Structural Steel Design, Concepts and Applications. In this class, we will talk about energy method, how energy method can be used to obtain the critical buckling stress for plates. In the previous class, we learned that the solution for critical loads for plates using differential equations d into dou power 4 w divided by dou x power 4 plus 2 into dou power 4 w by dou x square dou y square plus dou power 4 w by dou y power 4 is equal to nx into dou square w by dou x square plus ny into dou square w by dou y square plus 2 nxy into dou square w by dou x dou y. Now this is the one-Karman equation and this is the differential equation of plate buckling under the action of in-plane forces nx, ny and nxy. Now setting ny equal to nxy equal to 0, we have d into dou power 4 w by dou x power 4 plus 2 into dou power 4 w by dou x square dou y square plus dou power 4 w by dou y power 4 is equal to nx into dou square w by dou x square. So this is the partial differential equation for the plate buckling subjected to uni-axial compression, as you can see from the picture down. The generic solution is given as nx critical is equal to k into pi square d by b square. Here d is the flexural rigidity per unit width of the plate defined as E h cube divided by 12 into 1 minus mu square, and k is the elastic plate buckling coefficient. K is given as mb by a plus n square a divided by mb the whole square, and m is defined as the aspect ratio, which is a by b. When we plot the elastic buckling coefficient k with respect to the aspect ratio a by b, we get a series of curves also known as Garland curves. Here we can see several curves where m equal to 1 you have a single curve here, and m equal to 2 and m equal to 3 and m equal to 4. We can observe that as the aspect ratio of the plate increases, the curves tend to flatten, and basically indicating that there is a lesser variation of k with respect to aspect ratio as the aspect ratio increases, and especially after the aspect ratio of 4, it tends to flatten out much more. So for minimum value of nx critical, which is n equal to 1, n represents the number of half sine waves in the direction perpendicular to the loading, and long plates where a by b greater than 4, k is given as 4.0. The critical load of a plate under uniform compression in one direction is given as nx critical equal to 4 into pi square d by b square. So here k defined as mb by a plus n square a by mb the whole square is a function of three things. The first thing is the aspect ratio of the plate, which is a by b. Number 2, it is a function of the boundary condition of the plate. And number 3, it is also a function of the applied loading condition. Now let us compare the elastic critical solutions of columns, beams and plates. So the elastic critical solution for columns is given as sigma critical equal to pi square e divided by kl by r the whole square, and m critical is given as pi square eiy divided by L sub Lt the whole square into root of iw by iy plus gj L sub Lt the whole square divided by pi square eiy. And for plates, it is given as sigma x equal to k into pi square e divided by 12 into 1 minus mu square b by t the whole square. The following are the factors that influence the elastic critical solution. For columns, it is the effective length factor and it depends on the boundary conditions. For beams, it is the effective length against lateral torsional buckling, also known as L sub Lt, and it depends on boundary conditions as well as the loading conditions. For plates, it depends upon the elastic plate buckling coefficient, which is a function of the boundary condition, loading condition as well as the aspect ratio of the plate defined as a by b. Now let us look at how we are going to solve this. So the type of differential equation for columns is based on ordinary differential equations ODE, and for beams also it is ordinary differential equation ODE, whereas for plates it is partial differential equations PDE. Now let us look at the ordinary differential equation for columns. We have used energy method for finding the critical load of columns for a generic cross section. So the pi value is given as a big equation, as you can see on the screen, and the solution for that equation is also in cubic form, as you can see below. Now let us move to the beams. Even in beams, we have used energy method for finding the critical moment of beams. Here the total potential energy is given as pi, and it is a big equation, and this is for the doubly symmetric cross section. Similarly, a much bigger equation is shown below. This is for monosymmetric sections about minor axis. When we solve the two, we get the elastic critical moment as mcr, which is given as pi square eiy divided by L sub Lt the whole square into root of iw by iy plus gj into L sub Lt the whole square divided by pi square eiy, which is for doubly symmetric sections. And much bigger equation is shown below in the screen, which is for monosymmetric sections about minor axis, which is a function of three values C1, C2 and C3. all of which have been described in the previous classes. Now let's look at the partial differential equation for the plates. The differential equation method is cumbersome for finding the critical load under different loading and support conditions. So energy method can be adopted to solve the plate buckling problems as well. Now let us find the energy method for finding the critical stress of plates. Now let us look at the energy equation for plate buckling. So this is a plate that is subjected to uni-axial compression Nx, and it is simply supported on all four sides, and the stress at any point is given on the right hand side of the figure. The total potential energy pi equal to U plus V, and U is defined as the strain energy stored in the deformed body, and it is related to the external work done. The external work done is given as half into force into displacement. Now let's multiply and divide with volume on the right hand side. So we have strain energy equal to half into force by area multiplied by displacement by length multiplied by volume. So this can be written as half into axial stress into axial strain into volume, and it can be mathematically represented as half into sigma by E into V is equal to sigma square by 2E into V. Now the strain energy is given as sigma square by 2E into volume V. Now this strain energy in the x direction is given as du1 is equal to sigma x square by 2E into dx, dy and dz. And in the y direction it is given as du2 equal to sigma y square by 2E into dx, dy, dz. The strain energy due to Poisson's effect is given as du3 equal to half into sigma x into minus mu into sigma y by E into dx, dy, dz, which can be written as minus mu into sigma y into sigma x divided by 2E into dx into dy into dz. Now the strain energy due to shear is given as du4 is equal to 1 by 2 into tau xy into tau xy by g into dx, dy and dz, and this g can be written as E by 2 into 1 plus mu. So when we substitute and reduce this equation, we get 1 plus mu into tau x square divided by E into dx, dy, dz. Now the strain energy stored inside a plate after bending is given as integral of minus h by 2 to h by 2, which is the integration in the thickness direction, and in the width direction it is 0 to B, and in the length direction it is 0 to A, du1 plus du2 plus du3 plus du4 into dx, dy and dz. Now this can be further simplified by substituting the values of du1, du2 and du3 and du4 above. So we also know that sigma x equal to minus Ez divided by 1 minus mu square into dou square w by dou x square plus mu into dou square w by dou y square. Similarly for sigma y and tau xy. So we can substitute all those values into the integral that is shown on the right hand side. We get the strain energy of the plate due to bending, which is given as U equal to d by 2 into 0 to B, 0 to A, dou square w by dou x square the whole square plus dou square w by dou y square the whole square plus 2 mu into dou square w by dou x square into dou square w by dou y square plus 2 into 1 minus mu into dou square w by dou x dou y the whole square dx, dy. And this derivation can be obtained from the Principles of Structural Stability Theory by Alexander Chages. It is a very classic textbook. Now the total potential energy is given as pi equal to U plus V. We have already found out the value of U. Now let's look at the potential energy due to external loads V. And to determine the potential energy of the external loads, the plate is considered to be made up of a series of longitudinal strips, as you can see on the picture on the right hand side. So we know that del sub B is equal to half into 0 to A dou w by dou x the whole square into dx. This was already discussed in the class on beams, and this is basically the actual shortening due to bending in the columns. You can see the arc length is S and the shortened length is L, and delta B is S minus L. So S is given as L plus 0 to L half into dx by dz the whole square into dz, and when we do the simplification we get delta B is equal to half into 0 to L dx by dz the whole square into dz. Here in columns the out of plane displacement is x, and hence dx by dz the whole square is coming inside the integral, whereas in the plates the out of plane displacement is w, and hence delta sub B is equal to half into 0 to A dou w by dou x the whole square into dx. Now for any strip, the potential energy is equal to the negative product of the force Nx into dy and the shortening of the strip in the x direction due to bending, which is delta sub B. So we have dV equal to minus Nx into dy into delta B, and we know that dV equal to minus Nx dy into half into 0 to A dou w by dou x the whole square into dx. So when we integrate it with respect to the width, we have v equal to minus 0 to b nx by 2 into dy into 0 to a dou w by dou x the whole square into dx. Now let us solve the problem of a simply supported plate subjected to uni-axial compression in the x direction. Now we have a simply supported plate on all sides and the uni-axial compression is nx, the length of the plate is a and the width of the plate is b. So the boundary conditions is given as at x equal to 0 and x equal to a, the lateral deflection w equal to 0 and the moment dou square w by dou x square is equal to 0. Similarly, at y equal to 0 and y equal to b, the lateral deflection w equal to 0 and the moment dou square w by dou y square is equal to 0. Now, where n is the uniformly distributed force acting along the two opposite edges, let us assume a lateral function w, which is also known as the deflection function, given as a into sin pi x by a into sin pi y by b. The first important thing is to check if the function satisfies the boundary conditions. So, at x equal to 0, w equal to a sin 0 into sin pi y by b, which is equal to 0. Similarly, dou square w by dou x square is equal to minus a into pi square by a square into sin 0 into sin pi y by b, which is again equal to 0. Now, at x equal to a, w equal to a sin 0 into sin pi y by b equal to 0 and dou square w by dou x square is again given as minus a into pi square by a square into sin pi a by a, which becomes sin pi, again this value is also 0. Now, at y equal to 0, w equal to 0 because sin 0 is 0 and similarly dou square w by dou y square contains the term sin into pi y by b and y equal to 0, so sin 0 becomes 0. So, dou square w by dou y square is also 0. Now, at y equal to b, w equal to a sin pi x by a into sin pi into b by b, which becomes sin pi, again it is 0. And dou square w by dou y square is given as minus a into pi square by b square into sin pi x by a into sin pi b by b, which is also equal to 0. Now, this function satisfies all the boundary conditions. We can proceed to calculate the critical load. So, the total potential energy of the plate is given as strain energy due to bending and the potential energy due to external loads V. So, now let us look at the strain energy due to bending, which is a big equation here as you can see, and this can be solved by compartmentalizing the entire equation into 4 different parts. So, the first part is given here and second part is the second term, third part and the fourth part. So, to evaluate this expression, the following derivatives w are needed. So, we have w equal to a sin pi x by a into sin pi y by b. So, dou w by dou x equal to a pi by a into cos pi x by a into sin pi y by b and dou square w by dou x square is given as minus a into pi square by a square into sin pi x by a into sin pi y by b. Similarly, for dou w by dou y and dou square w by dou x square, we have the similar expressions here. And for dou square w by dou x dou y, we have a into pi square by ab into cos pi x by a into cos pi y by b. Now, let us evaluate the first integral, which is 0 to b 0 to a dou square w by dou x square the whole square into dx into dy. So, when we substitute the values, we can simply evaluate this by knowing that 0 to a sin pi x by a the whole square is nothing but a by 2 and similarly integral of 0 to b sin pi y by b the whole square is equal to b by 2. These different integrals are shown at the bottom of the screen here. So, when we substitute it, we get pi power 4 into a square b divided by 4a cube, which is equation 1. For equation 2, we have 0 to b 0 to a dou square w by dou y square the whole square into dx dy. Again, we substitute the value for dou square w by dou y square. We simplify this further and we get a value which is pi power 4 a square into a divided by 4b cube. And for equation 3, which is 0 to b 0 to a dou square w by dou x square into dou square w by dou y square into dx into dy, we have a big equation when we substitute the values of dou square w by dou x square and dou square w by dou y square. We can simplify this further. When we simplify this, we get the value 2 mu into pi power 4 into a square divided by 4ab. Now, integral 4 is given as 0 to b 0 to a 2 into 1 minus mu into dou square w by dou x dou y the whole square into dx into dy. Again, we substitute the value of dou square w by dou x dou y in this equation above. When we simplify this further, we get the value of 2 into 1 minus mu into a square into pi power 4 divided by a square b square into a by 2 into b by 2. Now, let us plug in all these equations into the strain energy equation. We get a big equation here. When we substitute this and taking the common, which is when pi power 4 and a square is taken as common terms outside, we can simplify this further by cancelling plus 2 mu by 4ab and minus 2 mu by 4ab. And next we multiply and divide with AB and we get an equation in the form 1 by a power 4 plus 1 by b power 4 plus 2 by a square b square, which can again be reduced as u equal to pi power 4 into a square d divided by ab by 8 into 1 by a square plus 1 by b square the whole square. So we have obtained the strain energy due to bending. Now let us look at the potential energy due to external loads V. The potential energy due to external loads V is given as minus n by 2 into integral of 0 to b and integral of 0 to a dou w by dou x the whole square into dx dy. And we know the value of w as a into sin pi x by a into sin pi y by b. So dou w by dou x equal to pi by a into cos pi x by a into sin pi y by b, which can be substituted in the above equation. When we simplify this further, we also know that 0 to b sin square pi y by b is equal to b by 2 and 0 to a cos square pi x by a equal to a by 2, and this simplifies the potential energy value as V equal to minus n by 8 into pi square b by a into a square. Now let us add the two together. To get the total potential energy, which is given as pi power 4 a square d into ab by 8 into 1 by a square plus 1 by b square the whole square minus n by 8 into pi square b by a into a square. In accordance with the concept of neutral equilibrium and the principle of stationary potential energy, the critical loading can be determined by finding the equilibrium in a slightly bent configuration for which the total potential energy has a stationary value. In order to accomplish this, we need to differentiate the total potential energy U plus V with respect to A, which is the capital A, and equate it to 0. So when we do so, we get the value n critical equal to pi square A square into D bracket open 1 by a square plus 1 by b square the whole square. And we can multiply and divide by b square and rearranging the terms and simplifying it further, we get pi square d into ab the whole square by b square into 1 by a square plus 1 by b square the whole square. On further simplifications, we get the value pi square d by b square into ab by a square plus ab by b square the whole square. N critical is given as pi square d by b square into b by a plus a by b the whole square. Now let us take the aspect ratio b by a is equal to 1.0. We get n critical equal to pi square d by b square into 1 plus 1 the whole square, which is nothing but 4 pi square d by b square. Now the critical stress is given as sigma critical equal to n critical by t. So we have 4 pi square d divided by t into b square, and substituting d as E h cube divided by 12 into 1 minus mu square, where h is nothing but the thickness. So this can be replaced as E t cube divided by 12 into 1 minus mu square. When we do so, we get sigma critical equal to 4 pi square E divided by 12 into 1 minus mu square into t by b the whole square, which can be rearranged as sigma critical equal to 4 pi square E divided by 12 into 1 minus mu square into b by t the whole square. Now K is the elastic plate buckling coefficient, which is given as 4.0. This indicates that the critical buckling stress obtained for uni-axial compression on all 4 sides simply supported using energy method, it is the same as the one that is derived using the differential equations. So this is the plate under biaxial uniform compression, as you can see here. Similarly, similar to the previous problem, the plate is simply supported on all 4 sides, except that the loading is in both directions, not in uni-axial compression, but it is biaxial uniform compression. Now here we make the assumption that Nx equal to Ny equal to N, which is uniformly distributed force acting along opposite edges. Let us assume the deflection function to be A into sin pi x by A into sin pi y by b, which is the same as the previous one. Here the deflection function is simply a function of the boundary conditions, not a function of the loading conditions, and hence the same deflection function that was used for uniaxial compression can also be used for biaxial compression. So the boundary conditions given are x equal to 0 and x equal to a, the lateral deflection w equal to 0, moment dou square w by dou x square equal to 0. Similarly, at y equal to 0 and y equal to b, the lateral deflection w equal to 0 and moment dou square w by dou y square equal to 0. So let us check if the function satisfies the boundary conditions. At x equal to 0, we know that w equal to 0, as you can see from the screen here, because sin 0 is 0. And similarly, for moment dou square w by dou x square is also 0, because sin 0 is 0. At x equal to a, w equal to a into sin pi a by a into sin pi y by b, and which is 0 because sin pi equal to 0. Similarly, dou square w by dou x square also contains the term sin pi x by a. So when we substitute x equal to a, again the term sin pi comes, so it becomes 0. Similarly, at y equal to 0, w equal to a sin pi x by a into sin of 0, which is actually equal to 0. And similarly, dou square w by dou y square also, when we substitute the term 0 in sin pi y by b, it becomes 0. And for y equal to b, W equal to A sin pi x by A into sin pi B by B. So, sin pi equal to 0 and hence this is also 0. Similarly, for dou square W by dou I square, which is the moment, sin pi B by B, which is equal to sin pi, and it is also equal to 0. Now, the function satisfies all the boundary conditions. So, we can proceed to calculate the critical load. Since the boundary conditions are same, the deflection function and the strain energy U remains the same. Hence, the strain energy due to bending is given as U equal to pi power 4 A square D by AB by 8 into 1 by A square plus 1 by B square the whole square, which is the same as what we derived for uni-axial compression. Now, the only change here is that the potential energy due to external loads due to biaxial compression will change, which is what we need to evaluate in this problem. So, now let us look at the potential energy due to external loads V. To determine the potential energy of the external loads, the plate is considered to be made up of a series of longitudinal strips as shown in the figure here, and this is for uni-axial compression, and Nx into dy is given here, and for any strip the potential energy is equal to the negative product of the axial shortening due to bending and the applied load in the corresponding direction. In this case, dV equal to minus Nx into dy into 1 by 2 into 0 to A dou W by dou x the whole square into dx, and V is given as minus 0 to B Nx by 2 into dy into integral of 0 to A dou W by dou x the whole square into dx dy. And this boils down to V equal to minus half into 0 to A 0 to B Nx into dou W by dou x the whole square into dx into dy. And this is the potential energy for a plate subjected to uniaxial compression. Now, for biaxial compression, we have V equal to minus half into 0 to A 0 to B Nx into dou W by dou x the whole square into dx into dy minus half into 0 to A 0 to B Ny into dou W by dou y the whole square into dx into dy. The second term is simply because it is also getting loaded in the y direction as well. Now, this can be further simplified assuming that Nx equal to Ny equal to N, and this equation can be written as V equal to minus N by 2 into 0 to A 0 to B dou W by dou x the whole square plus dou W by dou y the whole square into dx into dy. Now, let us differentiate with respect to x. So, dou W by dou x equal to A into pi by A into cos pi x by A into sin pi y by B, and dou W by dou y equal to A into pi by B into sin pi x by A into cos pi y by B. We can substitute both these values into the potential energy equation and we get a big equation here. We also know that integral of 0 to A sin square pi x by A equal to A by 2 and integral of 0 to A cos square pi x by A equal to A by 2. Similarly, 0 to B sin square pi y by B equal to B by 2 and integral of 0 to B cos square pi y by B equal to B by 2. Using these simplified integrals, we can substitute back into this equation and we get the value as V equal to minus N into A square pi square by 2AB the whole square into 2AB by 4, which gives rise to the value V equal to minus N A square pi square by 4AB. Now, let us substitute that in the total potential energy equation U plus V. We have U plus V equal to pi power 4 into A square D by AB by 8 into 1 by A square plus 1 by B square the whole square minus N A square pi square by 4AB. So, now assuming A equal to B, which means that it is a square plate, which is equal to pi power 4 A square D divided by 8 A square into 4 minus N into A square into pi square by 4, which is equal to pi power 4 A square D by 2 A square minus N A square pi square by 4. Now, we can find out the Nx value, which is the critical buckling load for the plate, by differentiating the total potential energy with respect to A, which is the capital A here. So, when we differentiate that, we have pi power 4 into 2A into D divided by 2A square, which is equal to N into 2A into pi square divided by 4. So, we have pi power 4 into D divided by 2A square is equal to N pi square by 4. So, we have N critical equal to 2 pi square D by A square, and where K is the elastic buckling coefficient, here it is given as 2.0. Now, the comparison of critical load for uniaxial and biaxial uniform compression can be observed here. Here, N critical equal to 2 pi square D by A square, where K is the elastic buckling coefficient given as 2.0, and for a plate under uniform compression, we have N critical equal to 4 pi square D by A square and K is the elastic buckling coefficient, and in this case it is 4.0. So, this indicates that the load capacity is increased twice when we move from biaxial compression to uniaxial compression, where the elastic buckling coefficient changes from 2 to 4. So, we have completed the portion on uniaxial as well as biaxial compression. We can use the same energy method for plates under various boundary conditions in the next class. Thank you very much.